Alright, so today we will be doing problem 11.6, which is dealing with a solenoid that has a changing magnetic field. Um, so for part A, we're asked to find the magnitude of E of the induced electric field in terms of R and dB dt. And dB dt is a constant value, and since the solenoid is changing, it has a changing magnetic field, dB dt is constant. So for part A, we use the formula given over here. The surface integral of E dl equals negative d flux dt. So we put that in. I use B for magnetic field. You can use M, whatever you want. But we know that flux equals the number of magnetic lines through a given area. So d flux equals the area times dB, and you can plug that in there. So then we get, and E is also constant along dl, and for since it's a solenoid, and it's an ideal solenoid, they're very tight circles. So it's E times 2 pi r equals, and since it's magnitude, we don't have to find whether or not it's negative, so we can ignore that, d dt of BA. So plugging in for this, we know that A is equal to, A of the circle equals pi r squared. So pi r squared dB dt equals E times 2 pi r. So then we get E equals r over 2 dB dt. For part B, you're asked to find the direction of the field lines of the induced electric field at point 1, point 2, and point 3. And I've drawn concentric circles to help us visualize if there were like imaginary wires there where the induced current would be taking place. For this, we will use the concept of the magnetic field is coming out of the page at us, and electric field is in the same direction as current. And since the current is flowing clockwise, because by using our right hand rule, we know that coming out of the page with our fingers, the current's going to be going that way. So the current's going to be going clockwise when it's at clockwise in a circle, to the right when it's at the top. So the E will be going clockwise as well. So at point 1, it'll be going clockwise, which is to the left. Point 2, it'll also be clockwise. And these are all tangent to the circle, because you don't want to draw a curved path, because field lines are never curved, they're straight, unless something's gone wrong with physics. So that's that. There are a few things you need to be careful about, though. Make sure it's in the right direction, and make sure you account that there is electric field outside of the solenoid. Otherwise, you can get points docked for that. Part C is very similar to Part A, except now you're outside of the solenoid, so R is greater than A. So the closed integral of E dot dl, we're going to be using the same formula except slightly different. D flux dt. We're going to use the same d flux equals AB, but now the only part of the radius that's accumulated that is affecting the flux is inside the solenoid, which is of radius A. So A equals pi a squared, little a squared b, dB, sorry. Then we plug that in, E 2 pi r, because E is still varying with R, equals pi a squared dB, sorry, that's a d, dB dt. The pi's cancel out on both sides, and then we get E equals a squared over 2r dB dt. Then for part D, we have a graph, and we use the equations. It's r and E. R is on the x-axis, E is on the y. Sorry. So yeah, we figure out in part A that when when you're inside the solenoid, E is r over 2 dB dt. So that varies with r. So that's going to be a straight constant line since dB dt is increasing as well. I'm sorry, dB dt is constant. B is increasing at a steady rate. So it's going to be a straight line till it reaches its maximum at r equals a, and these lines are 2a and 3a. So this is its maximum at r equals a. Then it goes down, because when E is outside of the solenoid, it's 1 over r. It varies with 1 over r, so it will be concave down. Concave up, and like this. And that's how you do 11.6.